Hello everyone, I wanted to talk about two ways to calculate delta H for a reaction, okay? And so remember this delta right here is change, and this H is enthalpy. So this is change in enthalpy. Sorry, I wrote over that. So change in enthalpy, that little knot is for standard conditions. And remember, for thermochemistry, standard conditions is 1 atm, 1 molar, and 25 degrees Celsius. So this is the change in enthalpy, or the whole energy all the energy change over a reaction. And I just put this right here to remind us that we're talking about specific reactions. Okay, so delta H naught, change in enthalpy, or all of the energy change at standard conditions if we run this reaction at 1 atm, so in the open atmosphere, 25 degrees Celsius, so at room temperature, and if those conditions are 1 molar, so if you have a liquid, it's at 1 molar or 1 mole per liter. Okay, now in my last video, I did Hess's law. So what I really want to do is focus on calculating this delta H naught of the reaction using this enthalpy of formation. Okay, so again, we have our delta H, which is, we'll just call it enthalpy, or that change in energy. That naught means the exact same thing. It means standard conditions. And then this F right here means formation. Okay, so we're using delta H naught of formation. And you find these on a table. Okay, so let's talk about what these values are first, and then I'll go through how to use them to calculate this delta H of the reaction. So delta H of formations is the heat or the energy that's generated by forming 1 mole of a compound from its elements. Okay, so carbon itself is an element, and so when you have an element, and carbon as graphite is an element, the delta H of formation of elements is 0 kilojoules per mole. Okay, so elements have 0 kilojoules per mole. I wanted to point out, though, that when you have an element that's more ordered, so graphite, carbon is the lowest energy state. Carbon and diamonds are more structured. They're in a very specific location. And because they're in that specific location, there's a little bit more energy for them to form, okay? So because of that, delta H of formation is 1.88 kilojoules per mole. So just a little bit of energy, okay? So this carbon takes a little bit, or carbon as a diamond takes a little bit more energy to form. So I'll just say a little energy. So carbon as the graphite is the lowest energy form. And so we talk about this as 0. It's kind of like our baseline, okay? And then to reorder and form that diamond, it takes a little bit more energy, okay? Now, if I were to look at a compound right here, like carbon disulfide, okay? When I look up carbon disulfide, the gas on a table, I find a delta H of formation of 115.3 kilojoules, or again, kilojoules per mole. Okay, this unit is interchangeable when we're talking about thermochemistry. Okay, so when on a table I look and I see this carbon disulfide and the delta H of formation values, what that means is the delta H is the heat generated by forming 1 mole of compound from its elements. So I take carbon disulfide and I'm forming 1 mole from its elements. So I kind of rip this thing apart. And this is all theoretical, so this is not how it's made in a lab. I mean, this compound might be, but not all of them will be. So when I rip this apart, I take the lowest energy of the carbon, which is graphite, and I take the lowest energy of the sulfur, which is the sulfate, I take the lowest energy sulfur, which is S8. Okay, so if I go get sulfur, it's in that S8 form. I balance the equation so that I have 1 mole of product. So I only need 1/4 of a mole of sulfur, and I need 1 mole of carbon. And when I do this reaction, the amount of heat that it generates is 115.3 kilojoules. Okay, so when you find these delta H of formation on the table, that's what it means. I'm breaking this thing down to its elements. Okay, so let's do an example where we're actually finding delta H of formation, or where we're finding delta H of the reaction from delta H of formation. Okay, so to do this, we are going to use this equation, right? So we have delta H, or enthalpy of the reaction, is equal to the sum of N, which is the number of moles, times the delta H of formation of all of the products. Okay, so you have to put all of the products, the number of moles times the delta H. We're going to add all of those together. That's going to be subtracted from the sum, again, of N is the number of moles of the delta H of formation for all of the reactants. So I always remember delta H naught of the reaction equals products minus reactants. Okay? So we're going to use this equation. Let me break this down to make it a little bit simpler. Okay? So here is our question right here. Use standard enthalpies of formation to determine delta H for the reaction. We have copper disulfide gas plus 3 moles of chlorine gas reacts to form carbon tetrachloride liquid plus disulfur dichloride liquid. Okay, and so I looked on a table and I found the corresponding heats of formation for every single one of these. Okay, when you do this, make sure it matches exactly. So I have carbon disulfide, and that's in a gas. Okay, so make sure it says gas, because sometimes you'll have different numbers if you have a gas or a liquid or a solid. Okay. Then I've looked at chlorine gas, and notice for chlorine gas, chlorine in its elemental state is Cl2, and so the delta H value for this is 0. I have carbon tetrachloride liquid, which is negative 135.4 kilojoules per mole. And I have disulfur dichloride, which is negative 16.7 kilojoules per mole. And again, liquid. So make sure you're matching all of these when you look these up in the table. Okay, so now what I do, after I have gone through and looked at my reaction and looked on a table and found every single reactant and every single product, I rewrite my reaction down. Okay, so I have my reaction written at the top. Then I have my N value and I have my delta H. So remember, and I'll just write this up here, delta H of the reaction was going to equal the sum of the products minus the sum of the reactants. Okay, so for each of those sums, what I'm doing is I'm multiplying N times delta H not F. And I should have probably put that reaction on this slide so you could see it. So when I'm doing this, what I do is I go through and I look at how many moles. So here I have 1 mole. Here I have 3 moles. Here I have 1 mole. And here I have 1 mole. Okay, so I've written down how many moles I have. Next, I take my delta H not of formation. So these are the values I found in my table. And I write them underneath every single one of my reactants and every single product. So I'm making a table to make it easier. Next, I take this value, N times delta H naught of formation. So I'm multiplying these two together. So when I take 1 mole and I multiply it by 115.3 kilojoules per mole, the moles cancel, and I'm left with 115.3 kilojoules. Next, I take 3 moles and multiply it by 0 kilojoules per mole. Moles cancel, and I'm left with 0 kilojoules. 1 mole times negative 135.4 kilojoules gives me negative 135.4 kilojoules. So my moles cancel. Last one, 1 mole times negative 16.7 kilojoules per mole gives me 16.7 kilojoules. So now I've gone through and I've done this calculation where I've taken number of moles times delta H of formation. And remember, I have to look at all the reactants together and all the products. So what I'm going to do here is add all of the reactants together. And over here, I'm going to take and add my products together. So here for my reactants, 115.3 kilojoules plus 0 kilojoules is 115.3 kilojoules for my reactants. When I add the products together, I get negative 152.1 kilojoules of products. So delta H for my reaction equals products minus reactants. So delta H naught of the reaction equals the product, so negative 152.1 kilojoules minus the reactants, and when I do that calculation, I get a delta H of negative 267.4 kilojoules. Okay, so laying this out helps me avoid a lot of math errors. Okay, I have my number of moles, I have my delta H of formation from the table. I multiply those two together and get all of these numbers in kilojoules, all of my reactants, all of my products. Next, I add these numbers together to get my total reactants. Then I add my products together to get the total energy of my products. Okay, last step is I find my delta H on the reaction by taking products minus reactants. So I find my product value, which is negative 152.1 kilojoules, and I'm going to subtract my reactant value, which is positive 115.3 kilojoules. So here, negative 152.1 minus a positive 115.3 kilojoules gives me a delta H on the reaction of negative 267.4 kilojoules. That negative says exothermic, so when this reaction happens, energy gets released. So that is how I go through and do and kind of separate this to find these delta H of the reactions. Let me know if you have any questions.